Now let us look at the next problem. Let rho as a function of r is given as q by pi r to the power 4 times r be the charge density distribution for a solid sphere of radius capital R and total charge q for a point P inside the sphere at a distance r1 from the center of the sphere. The magnitude of the electric field is, okay. Now let us say you have this sphere and it has got a charge density, that means it is a variable density rho r, so where r is the distance from the center O. Okay, now we have to find out what is the electric field at any point P inside this sphere. Okay, we have to find out electric field E inside this sphere. Now from symmetry we know that, let us say we take a small sphere of radius r where r is less than capital R, then the electric field will be radially outwards at each and every point on this sphere. Okay, so the total flux that will come out of this small sphere, which we can assume to be a Gaussian sphere, Gaussian surface, then this total flux will be given by surface integral E dot ds. Now this total flux will be given will be equal to E, because E is constant and at every point ds is making an angle 0 degree with the electric field vector E. Okay, because electric field is radially outward. So if we take the integral of ds, it will be 4 pi r square. Okay, so E into 4 pi r square will be the total flux that will come out of it. From Gauss theorem, this flux will be equal to charge enclosed by the Gaussian surface upon epsilon naught. Okay, now if this is the case, now the only thing that is remaining is to find out what is the charge enclosed inside this small sphere. What is the total charge which is enclosed in this sphere? Okay, now we know that charge density is a function of distance r. Okay, now if we find out what is the total charge in a small elemental spherical shell of radius small r and thickness dr. Okay, it has got a thickness, the shell has got a thickness dr and its radius is r, then the volume of the small elemental spherical shell will be given by 4 pi r square, that is surface area, into dr, that is thickness. Now the charge that this small spherical shell will have will be equal to density, charge density rho into dV. Okay, what is rho? Rho is given as q by pi r to the power 4 times r, and dV is 4 pi small r square dr. Okay, now this term becomes pi will cancel out and we will have q 4q by r to the power 4 r cube dr. This is small elemental charge. Now if we integrate this charge with the limits of r from r equal to 0 to r1, we will get the total charge enclosed. Okay, now this term is constant and r cube dr will give you r to the power 4 by 4 with limits 0 to r1. Okay, so this is total charge Q enclosed. So Q enclosed will be equal to Q upon r to the power 4 into r1 to the power 4. This 4 will cancel out. Okay, now we have flux enclosed equal to E into 4 pi r1 square, which should be equal to Q enclosed upon epsilon naught, or E equal to Q enclosed upon 4 pi epsilon naught r1 square. Now if you substitute the values of Q enclosed, we will get Q upon 4 pi epsilon naught r1 square r to the power 4 into r1 to the power 4. This will be now equal to Q upon 4 pi epsilon naught r to the power 4 into r1 squared. So among the four options, option C is the correct one. Okay, option C is the correct one.